Welcome back to class time. It's now time for CAPE Chemistry. I am your teacher, Ricardo Price. Today's topic is forces of attraction. Let's get into it. Now, before we get into today's lesson, let's take a look at the objectives set out in the CAPE Chemistry syllabus. Now, some of these objectives were accomplished last week, but I'll still run through. Now, last week we looked at what is dative covalent bonding, and we described dative covalent bonding as a covalent bond, and we know that a bond contains two electrons. Now, in a covalent bond, these electrons are shared between the atoms, meaning that one atom gives one electron to the bond and the other atom gives one electron to the bond. But in a dative covalent bond, both of those electrons are coming from one of the atoms. Now, we also described the origins of intermolecular forces, specifically the hydrogen bonding interaction, the permanent dipole, and van der Waals forces of attraction. And we described hydrogen bonding as an interaction, an electrostatic interaction between a hydrogen atom that is attached to an electronegative element and it is interacting with another electronegative element. An example of a molecule that exhibits hydrogen bonding is water. There's also protein and DNA. The permanent dipole, we describe this as a molecule in which one of the atoms is much more electronegative than the other atom. An example of this would be HCl. We described the van der Waals instantaneous dipole or an induced dipole. A molecule that exhibits this would be bromine, where the molecules come together and one molecule induces the other molecule to have a dipole moment. So, last week we looked at VSEPR, but we didn't get to finish this concept. So the objectives for today is to finish VSEPR and predict the shapes and bond angles in simple molecules. And we also hope to explain the shapes and bond angles in simple organic molecules and make reference to hybridization and resonance. Now, so let's take a look at VSEPR theory. For this section of the lesson, you guys will need to get your pens and your pencils and write down the steps in predicting the shape. You might not understand while writing down the steps, but we'll work a few examples and it will become a bit clearer for you guys. Now, what is VSEPR? This is valence shell electron pair repulsion theory. So the concept is based strongly on electron-electron repulsion. Now, it says that this is a concept used in chemistry to predict the shapes and geometries of molecules. The premise is based on electron-electron repulsion, as I just said. But before we get into VSEPR theory and the steps to predicting the shapes, let's define a few terms. Now, what is a lone pair? A lone pair is simply a pair of electrons on an atom. What is a bonding pair? A bonding pair is a shared pair of electrons in a covalent bond. Now let's move to the board for you guys to clearly see what I mean by a lone pair versus a bonding pair. Now, so with this molecule here, this is just a molecule that I made up, a molecule XYZ. On X, you can see that X has two lone pairs of electrons sitting on top of it. X also has two bonds. X is bonded to Y and X is bonded to Z. Now, we know that electrons make up bonds. Each bond has two electrons in it. So this bond right here has two electrons in it like that. Right? So these electrons making up the bond is called the bonding pair. It also has another bond right here, and this bond also has two electrons. Therefore, this bond, the total bonding electrons in this molecule is 1, 2, 3, 4. So it has 4 bonding electrons and 2 lone pairs, right? So that's what I mean by a lone pair and a bonding pair, because I'll be making references to these terms quite a lot in VSEPR theory. Now let's get back to the smartboard. Now, lone pairs of electrons repel other lone pairs of electrons as well as bonding pairs, right? So what do I mean by this? I mean, if you have 2 lone pairs of electrons sitting right next to each other, the repulsion would be very great, right? The electrons don't like other electrons. They're both negatively charged, and we know that opposite charges attract each other. So if you should have 2 lone pairs right next to each other, they will repel each other. And if you should have a lone pair next to a bonding pair, those will repel as well, because the bonding pair also has electrons in it. Now, let's get into the steps on how to predict the shapes of molecules. The first thing that we should do, and you guys should write down this, this will be repeated on One Spot Media as well as YouTube, so you can either take a picture of the screen, write it down fast if you can do that, or rewatch it on YouTube, pause the video, and write down the steps. The first step says identify the central atom, and the central atom is usually the least electronegative element. The next step says draw the molecule in the simplest possible geometry with all the atoms as far from each other as possible. Now, why did we say this? This is because the bonds in the molecule have electrons in them, and you have to put the electrons as far away from each other as you possibly can. So we draw the molecule in the simplest possible geometry with the outer atoms as far from each other as possible to reduce electron-electron repulsion. Now, the next step says we should sum the number of valence electrons in each atom and subtract the bonding electrons from this total. So, for instance, you have water. Water has hydrogen, it has 2 hydrogens and an oxygen. The valence electrons in oxygen has 6 valence electrons, hydrogen has 1, but there are 2 hydrogens, so that's 2 plus 6, so the total valence electron count in water is 8, the 6 from oxygen and the 2 from the hydrogens. So we sum the total valence electrons, and then when we get that total, we should subtract the number of bonding electrons from that total. The remainder that you get once you subtract the bonding electrons, you should add those to the outer atoms first. And if you have any excess, that's when you put it on the central atom. So this says the remainder of the electrons should be added to the outer atoms first until they have their octet of electrons, or until their valence energy level is completely full. Then, if there is excess electrons, we move to the central atom. The last step says, now to apply the VSEPR theory, we use the lone pairs to repel the bonding pairs, and this will change the shape of the molecule. So this is the last step that actually determines the shapes of these molecules. Now, we will work some examples. We will predict the molecular geometry of BF3 and H2O. But before we actually do that, it's important to note that a lone pair interaction or repulsion is a lot stronger than a lone pair bonding pair repulsion. And that is because the lone pairs are just sitting on top of the atom, right? They're not involved in bonding. Bonding electrons are more dispersed or spread over a larger area. It's a bit diffused. So the interaction between 2 bonding pairs is not as strong as the interaction between 2 lone pairs, right? The charges are a lot greater on the lone pair, and it's a bit diffused in the bonding pair. So 2 lone pairs right next to each other would repel each other greatly. If a lone pair is next to a bonding pair, it would repel each other as well, but not as strongly as if two lone pairs were next to each other. And bonding pairs also repel bonding pairs, but not as strong as a lone pair repulsion. And I'll show you what I mean with some of these examples. Now, the first one says we should predict the molecular geometry of BF3. Hopefully you guys have recorded the steps and we'll do it right now. So we'll move to the board. So, in a question like this, your teacher, or on the question paper, they'll give you the molecular formula, BF3. And they'll say to you, predict the molecular geometry of this molecule. Now, the first step says that we should identify the central atom. The central atom is usually the most electronegative, the least electronegative atom. Here, boron is a lot less electronegative than fluorine. Fluorine is the most electronegative element, right? So I'll use boron as my central atom. There's another way of predicting the central atom. In this molecule BF3, there are 3 fluorine atoms and only 1 boron. The central atom is the one with the fewest number, usually. So in this case, boron, 1 boron and 3 fluorine. So boron would be my central atom. And then the next step says that we should arrange the molecule in the simplest possible geometry with the bonding pairs as far from each other as possible. So there are 3 bonding pairs. So I'm going to arrange it like this. They're as far from each other as possible, right? The next step says that we should sum the valence electrons on each atom. So boron, hydrogen, helium, lithium, beryllium, boron. Boron is the 5th element. The first 2 electrons would be on the first energy level. And then it would have 1, 2, 3 valence electrons. So boron has 3 valence electrons, and we know that fluorine is in group 7. It has 7 valence electrons. But there are 3 fluorine atoms. Therefore, this would equal to 21. So when we sum the total valence electrons, it's 21 plus 3, and that is equal to 24. So this is the total valence electron count in the molecule. Now, there are 3 bonds. There are 3 bonds in the molecule, and we know that each bond has 2 electrons in it. So since there are 3 bonds, we know that there are 6 bonding electrons in this molecule. So we have to subtract that 6 from the total, and we would end up with 18 electrons remaining, because those 6 electrons had to go to making up the bonds. Now, what do we do with the remainder, with this remainder of 18 electrons? We have to put them on the outer atoms first and ensure that their octets are completely filled, and then we move on to the central atom if we have excess electrons remaining. Now, let's focus on this fluorine atom. This fluorine atom has 1 bond, and that 1 bond has 2 electrons in it. So those 2 electrons count as valence electrons. And we know that fluorine can hold a maximum of 8 electrons in its valence energy level. So therefore, since it has 2 electrons, it needs 6 more to get that 8. So I give it that 6. 1, 2, 3, 4, 5, 6. And each fluorine is in the same situation. So I have to do the same thing for the other 2. So this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. So we used up all 18 electrons. So we have no excess electrons to put on the boron. Therefore, the molecule retains its shape. So this shape that you see here is the shape of BF3. If there was a lone pair on the boron, the shape would be distorted because the lone pair would start pushing down on the bonding pairs and it would change the shape of BF3. So therefore, BF3 is what we call a trigonal planar. It has a trigonal planar geometry. And the bond angles between BF3 is 120 degrees. Now it's important for you guys to know the shapes of these molecules as well as the bond angles. So if your teacher tells you that you have a trigonal planar molecule and or if your teacher asks you what is the bond angle of that specific shape, you'd have to know. Now let's move back to the smartboard. So we'll be moving back and forth between the smartboard and the whiteboard. Now you can see the bond angles between BF3. Right? Now, for water, the shape of water is what we call a V-shaped. And you can see it here on the screen. And the bond angles between water is 104.5. And I'll show you why the bond angle in water is less than that for BF3. Okay, so water is H2O. So I'll use oxygen as my central atom. And to draw it in the simplest possible geometry, I draw it like this. I draw it straight, linear, right? Now, I know that oxygen has a valence electron count of 6. Hydrogen has a valence electron count of 1, but there are 2. So, it's 6 plus 2 is equal to 8. However, there are 2 bonds. Therefore, there are 4 bonding electrons. So 8 minus 4 is equal to 4. So I have 4 electrons to put on these atoms. Now, the first thing that somebody would do is to put these 4 electrons on the hydrogens first. But hydrogen, the valence electron on hydrogen can only hold 2 electrons. And it already has those 2 electrons because it's sharing those 2 electrons within this covalent bond. Therefore, the hydrogens are fine. They don't need any electrons. So we have to put these 4 electrons on the oxygen. Like that. Now, what would happen is that you would have the lone pairs repelling each other. This is kind of small, but bear with me. The lone pairs would repel each other and push each other apart. And in so doing, it would also repel the bonding pairs. And what happens is that water develops this shape, where the lone pairs are over here, are pushed apart from each other, and the bonding pairs are pushed down into a V shape. And you can see the V. So it's V-shaped. And the bond angle is 104.5 degrees. So you can see the difference that the lone pairs of electrons have or make on these molecules. Put back these. Now, let's look at the shapes of some other molecules. Let's look at methane. Now, methane has a tetrahedral geometry, right? The bond angles within methane is 109.5 degrees. And you can figure out the shape of methane using VSEPR theory. So I'll allow you guys to practice with methane. However, I'll do some of the more difficult ones. So it's important to remember the shape. As I said, the shape here is tetrahedral. The bond angle between each CH bond is 109.5. Now let's look at BeCl2. BeCl2 has what we call a linear geometry. And you can see that it's linear, it maps out a line, right? And the bond angle here is 180 degrees, right? Now, I'll do ammonia and SF6 for you guys. With ammonia, what is the molecular formula for ammonia? The molecular formula for ammonia is NH3. So I want you guys to write NH3 in your books, because we're going to predict the molecular geometry. Now, so we're dealing with ammonia, NH3. Now, the central atom here is nitrogen. There's only one nitrogen and 3 hydrogens. So I'm going to write it like this. NHHH. A simple symmetrical geometry, right? So what is the valence? How many valence electrons does nitrogen have? So hydrogen, helium, lithium, beryllium, boron, carbon, nitrogen. The first 2 electrons are in the first energy level, so nitrogen has 5 valence electrons. So nitrogen donates 5, hydrogen donates 1, but there are 3 hydrogen atoms. So hydrogen gives 3. So that's a total of 8. But we have 3 bonds. That means 6 bonding electrons. So we have to subtract 6. So we have 2 electrons remaining. The hydrogens are okay. They have their 2 electrons in their valence energy level. Therefore, these 2 electrons have to be put on the central atom. Once we put those on the central atom, what happens? You know what happens. Electron-electron repulsion, because this is VSEPR theory. Valence shell electron pair repulsion theory. The theory is centered around this concept. So the lone pairs repel the bonding pairs and push them down, push them closer together. The bonding pairs would rather be closer to other bonding pairs than to be close to a lone pair, essentially. So what happens is that the lone pair pushes the bonding pairs closer together. So you end up with a shape like this, where you have the lone pairs on the top, and the hydrogens down here. The wedge means that it's coming out of the board towards you. The hashed line means that it's going into the board, behind the plane of the board. So this is kind of a 3D representation of something like this. And this is a pyramidal structure. A pyramidal structure. Right. So, the pyramidal structure and the bond angle here is 107.8 degrees. And this is so because of the lone pair. So the lone pair essentially pushes these bonding pairs together. So if the central atom has a lone pair on it, this will happen. Now let's look at SF6. SF6. Now, how many valence electrons does sulfur have? Sulfur has 6 valence electrons. Fluorine has 7, but there are 6 of them, so that 6 times 7 is 42. So we have 42 electrons coming from fluorine. sulfur has 6. When we sum those, we'll get 48. Let me separate these two so you don't get confused. So you have 48. Now, I should have drawn this before. F, 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 F. Okay, so when you have 6 atoms around a central atom, I first draw it in this geometry to ensure that the atoms are as far as from each other as possible. Now, looking at this, you can see that you have 1, 2, 3, 4, 5, 6. 6 bonds. Therefore, you have 12 bonding electrons. So if we should subtract that, we would get 36 electrons remaining. Now, this means that we have 36 electrons to put on these outer atoms. So let's start with fluorine, this fluorine. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, and 36. So we used up all 36 electrons. We used up all 36 electrons on the fluorine. Thus, we have no more electrons to put on the sulfur. Therefore, the shape remains the same. So, the shape of SF6 is octahedral. The bond angle is 90 degrees. And just to note, you guys should remember the shapes and the bond angles of these molecules. Now, let's get into the shapes of organic compounds. Now, what is an organic compound? Now, an organic compound or an organic molecule is a molecule consisting of carbon atoms covalently bonded to each other. And it also has carbon atoms covalently bonded to hydrogen atoms. If the molecule only has carbon and hydrogen bonds, then it can be referred to as a hydrocarbon. Some organic compounds possess outer atoms such as oxygen, nitrogen, sulfur, phosphorus, and halogens. Proteins are organic compounds because they have carbon and hydrogens in them. And we know that proteins have oxygen and nitrogen and sulfur as well. But a hydrocarbon is one that only contains carbon and hydrogen in its structure. Now, these organic compounds, they can have multiple bonds or single bonds. The ones that only have single bonds are termed alkanes. The simplest alkane is methane. It has a carbon atom covalently bonded to 4 other atoms, right? I'll get into the shapes of these. Alkanes soon. Now, you have methane. Sorry about that. So, you have methane, ethane, propane, and butane. Ethane is a 2-carbon alkane, propane is a 3-carbon alkane, butane is a 4-carbon alkane. Now, ethene is a 2-carbon alkene. So when you have organic compounds that contain double bonds, they're no longer called alkanes, they're called alkenes, right? So a 2-carbon alkene, which is the simplest alkene, is called ethene. The 3-carbon alkene is called propene, and the 4-carbon alkene is called butene. Now, you can have organic compounds bearing triple bonds as well, and these are called alkynes, and they have a linear shape. You can see it on the diagram, the E with ethine, right? It has a triple bond and it has a linear geometry. What's the bond angle? It's 180 degrees because it's linear. Now, with ethene, the bond angle is 120 degrees between the CHs, right? And it has a trigonal type geometry, while the alkanes have a tetrahedral geometry. And we know the bond angles with tetrahedral compounds. It's 109.5. That's why we taught VSEPR before we got into this. So we can see the shapes of the molecules here. Methane, 109.5 with a tetrahedral geometry. You can see the alkene with the bond angle of 120 degrees with a trigonal type geometry. And that's the same for benzene as well. Benzene has a bond angle of 120 degrees between the CH and the CC bonds. And we can see the alkyne at the end with its linear geometry, and the bond angle in the alkyne is 180 degrees. Now let's get into hybridization and what hybridization is. Hybridization is essentially the mixing of atomic orbitals to form new hybrid orbitals, right? What do I mean by that? Let's look at carbon, because carbon is an atom that exhibits hybridization. Now, carbon has an electronic configuration of 1s2, 2s2, 2p2. Now, when is an orbital considered stable? An orbital is considered stable if it is completely full or half filled, right? So let's look at the electronic configuration of carbon again. It's 1s2, 2s2, 2p2. And we're focusing on the valence energy level. The 2s is completely full. The 2p is neither filled nor is it half filled. It has 2 electrons in it. But we know that the 2s orbital is very close in energy to the 2p, thus an electron can jump from the 2s to the 2p. And we see that right here. We have the 2s and the 2p. An electron can transition from the 2s to the 2p to generate 4 new hybrid orbitals. It's hybrid because they've mixed, the 2s mixed with the 2p to generate these 4 hybrid orbitals. And these are called sp3 orbitals. Why sp3? Because you have 1s and 3p orbitals mixing to generate this new hybrid orbitals. Notice they kind of have a look like a p orbital. It kind of looks like a p orbital. And that's because it has p orbitals in it. It's 3p orbitals mixing with 1 s orbital. So the hybrid orbital will look like a p orbital. And this is how it looks. So alkanes are sp3 hybridized. Each of these sp3 lobes can be bonded to another carbon or a hydrogen. So this is the hybridization state of carbon in alkanes. Let's look at alkenes. So you have an electronic transition from the 2s to the 2p, right? With alkenes, you only have 2 of the p orbitals mixing with the s orbital, and you can see the unmixed p orbitals still in the same position, right? So when 1 s orbital and 2 p orbitals mix, we generate what we call an sp2 hybridized orbital. And you can see, if you look at the bottom, the diagram at the bottom, you can see the unmixed p orbital there in orange, showing that it didn't mix, it's still there, right? And you have 3 new hybrid orbitals in green, which are sp2 orbitals, and this is the hybridization state of alkenes. Now, when you have one s orbital and one p orbital mixing, this generates what we call an sp orbital. Makes sense? One s, one p. Right? Therefore, you have two unhybridized p orbitals there. And these p orbitals can overlap with other p orbitals. And this is what generates the triple bond. Right? So alkynes are sp hybridized. And remember the shapes of these molecules. Alkynes, linear, 180 degrees between for the bond angles. Alkenes are trigonal in shape. The bond angles are 120. With alkanes, it's tetrahedral, and the bond angles are 109.5. So it's important to remember the shapes of these molecules as well as their bond angles. So with the sp hybridized orbital, you have the p orbitals. Now these p orbitals, as you can see here in red and in blue, once they come in contact with other p orbitals, they can overlap. So you can see the red orbital overlapping with the other red orbital, the blue orbital overlapping with the other blue orbital to generate something like this, where you can see them fused together. And that is what actually generates the triple bond. And the same is true for the alkene. Now, that's the time we have for CAPE Chemistry. Until then, keep safe. Remember to wash your hands, sanitize, and wear your masks.